You and test on this. Good in the back. Good. Okay. Great. Thanks for having me. And I am excited to talk about James Webb today. It's been a long time coming, it feels like, to talk about high-redshift supernova discovery with James Webb. And these are really the first types of results that we're getting. And it's early days yet, but there's still some really cool stuff to talk about. So I'm going to give a little tour of what we've been doing in transient science with James Webb. A little background, of course, and the types of constraints that we had at the beginning of launch and where we've gotten to now, where we're trying to get to in the future. Talk a lot about it's been now about 3 years of James Webb and the progression that we've had up to this point, and now what the stage is sort of set for the future of high-redshift supernova discovery. I'm going to go through some of the highlights and then actually take a left turn into strong gravitational lensing. So this is the other half of what I do, is not just normal high-redshift supernovae, but also strongly lensed supernovae. So we've had some success on that. This just stopped changing slides, so I guess I'll use this. We've had some success finding strongly lensed supernovae with James Webb, so I'll just show some of those, kind of the other exotic cool stuff that James Webb's doing, and then talk a little bit about the next stages, both for James Webb and other upcoming missions. Let me see if this, yep, okay, suddenly started working again. So a couple slides on background. On the top level, just supernovae in general. I'm mostly going to end up talking about the left half of this image, but I'll say that the end result of higher mass stars is what we call core collapse supernovae, and they are the most common type of supernova that we observe. The left half of this is for lower mass stars, which turn into white dwarfs, and if they have a companion, whether that be another white dwarf or a main sequence star, still up for debate, but that can result in what we call this Type Ia supernova explosion. So I'm going to end up talking mostly about that Type Ia side because that's what I do, but we've been observing lots of core collapse supernovae, as you imagine. I have some extra slides on that. If I have time or you have questions about it, I'm happy to move into that at the end here. So the actual way that we kind of separate these ends up being from their spectra. So that Type Ia on the top, the main thing that we look for is a strong absorption of silicon. It's in the green. And then core collapse, there's a bazillion subtypes, but the main three that we look at are Type 2 on the bottom, so we look for strong hydrogen, and then these stripped envelope supernovae, so ones where the hydrogen is gone, but we see helium, and then both hydrogen and helium are absent. So this is kind of our big picture of supernovae with a bazillion subtypes that I'm ignoring, and like I said, I'm going to focus mostly on Type Ias, but like I said, if you're interested in core collapse, ask about it at the end, because I do have some cool slides on that. So the reason that Type Ia supernovae are very well studied, and this is I'll just switch to this, is because they are one of our best cosmological probes. So the way that these are normally used is as what we call these standard candles. So this is what you'd imagine a standard candle would look like, is if you took a bunch of Type Ia supernovae at a variety of distances, so imagine each of the colored points corresponds to a supernova at different distances. It doesn't matter if you correct for that distance, they have the same intrinsic light curve shape. They're the same brightness, they behave the same. That's what a standard candle looks like. They actually look more like this, where it turns out that less luminous supernovae, Type Ia supernovae, fade a little bit faster, and vice versa, which means that in order to actually use these for cosmology, we need to turn them into something which we like to call standardizable candles, which means we have to observe a light curve, determine whether these are fading faster or more slowly, make that correction so that they become standard candles. And that's exactly what happens, which is what this right-hand side is. It's after doing that correction. So these are actually very good standardizable candles. They are not precisely standard candles. So the process here is basically find the Type Ia supernova by observing it with a spectrum that shows it's Type Ia, get a light curve, determine how quickly it's fading, make that correction. Turns out there's a secondary correction. Is it bluer or redder? But that all comes from the light curve. And then put it on what we call a Hubble diagram, which is just that distance as a function of redshift. So going back to the 90s, if you take distances of Type Ia supernovae as a function of redshift and compare them to different cosmological models, you'll see something like this. And just relative to that same set of models, same type of thing here. This, looking over on the right-hand side of these different models diverging and going through these set of points on here, this is the original discovery of accelerated expansion and the inferred presence of something called dark energy, right? So this is kind of a process of using Type Ia supernovae for cosmology. The question that I'm kind of addressing here and what James Webb is really going to be valuable for is what about these supernovae that we're using? What if the population at high redshift is just significantly different than those at low redshift? I'll start off by saying that that's not enough to just do away with dark energy, but it could significantly bias what we understand about dark energy. Is dark energy changing with time? Is it getting stronger with redshift or weaker with redshift? If the population of Type Ia supernovae is different at different redshifts, then that will just significantly bias the measurements that we are currently planning to make over the next 5 to 10 years. So looking at this in a slightly different way, this is same diagram as this. So it's redshift and distance relative to a cosmological model that is constant dark energy. So this is the black line there is dark energy, but it's the cosmological constant. There's no variability with redshift. The shaded black region here is kind of our uncertainty right now from our various cosmological measurements on how much dark energy could change with redshift. Then this green, which is actually a little hard to see on this screen, but this green shaded region is what if there's some progenitor metallicity evolution with redshift that changes the way in which Type Ia supernovae work, and they're just systematically getting fainter or brighter with redshift. At about 1.5, redshift 1.5, you transition from dark energy dominated to dark matter dominated. And in this regime, you can start to see that for dark energy, even if dark energy is changing with redshift, after about 1.5, it's a very flat behavior in terms of what you'd expect to see with Type Ia supernovae. So even if dark energy is changing, if nothing else is changing, then you'd expect to just see 1A distances that just kind of stay along this flat line. If you continue to go to high redshift and Type Ia supernovae are changing significantly, then regardless of what's happening with dark energy, we would expect to see some drastic increase at high redshift. So basically, high redshift Type Ia supernovae, they have a lot of leverage for this question of whether Type Ia supernovae are changing significantly with redshift. You could do that measurement here, but you'd have to do it very precisely to disentangle whether it's 1A is changing or dark energy changing. But if you could do it out here, you have a little bit more leverage. So this is simulation of what that would look like. If you measured a relatively small sample, this is just 10, you could find yourself in one of these two scenarios, either on this red scenario where you're identifying, yes, in fact, some global property changing with redshift is in fact impacting our Type Ia supernova distances, or you could end up in this blue scenario where we say, okay, things might be changing, but they are not impacting our 1As. We can use them with impunity. Our current sample of spectroscopic supernovae, Type Ia supernovae, looks like this. So this is the same plot now, just in log space, just to blow it up here. So we've really filled out the redshift less than 1 diagram here with over 1,000 Type Ia supernovae over the years. If we zoom in here on the right side, then this is redshifts greater than 1.5. You'll see that we have one that is in the spectroscopic sample, and then these are photometrically classified, and then these are gravitationally lensed. Gravitational lensing, great for making things brighter, but brings its own set of systematics into the equation. So we'd really like to increase this sample. I also wanted to just mention that this one redshift 1.6 spectroscopically confirmed 1A, this is what that looks like. So on the right here, this is that redshift 1.6 classification. It's a Hubble classification. It's okay. So this is where we're starting, basically, in terms of going to higher redshift. This was the limit before the launch of James Webb. So this is the area we're trying to get to, and for a variety of reasons, but one of them being this high leverage on possible evolution for 1As. The problem has been, if you look at this little cartoon SED, most of the flux for a type 1a is in this kind of 4 to 5,000 angstrom range, which at redshift 2 brings you basically to the limit of Hubble. And so that's just been kind of the barrier between sensitivity and wavelength. You just can't really break that barrier. So of course, that leads you to the James Webb Space Telescope, which has been very, very cool to work with. A little cartoon of the universe here with our various regimes. This works about half the time of supernova discovery. So in this kind of low redshift less than 1, we are finding thousands of supernovae per year. This will really explode with things like Rubin upcoming, right? All in this kind of lower intermediate redshift range. And then Hubble was what was giving us that redshift 1 to 2 range for a while, with a couple of dozen discoveries in that range, with the spectroscopic sample, as I just said, kind of grounding out at redshift 1.5 because of both sensitivity and wavelength. So this has been the promise of James Webb for a while, is that this is what will extend this type of discovery beyond redshift 2 out to the early universe. And beyond things like Type Ia supernova cosmology, this is really exciting for things like probing stellar populations in the very early universe, where even with something like James Webb, without a supernova, you just can't do that very effectively, looking at individual stars. And so this has kind of been the James Webb promise. So in the early days, this launched at the end of 2021. The first data was released in July of 2022. And that was pretty frantic of just kind of trying to figure out the pipeline, trying to figure out what the data products looked like, blinking things back and forth, just looking for things that changed. We had no real science goals at that point, I would say. We were just sort of looking for supernovae for the sake of looking for them. We had no resources to follow anything up, because anything you discover with James Webb can only be followed by James Webb. So this is the transient name server, which is where most transients are reported. And you can see down here, on July 16th of 2022, which just after the first data was released. This is our group reporting the first transient discovery with James Webb. We had no spectrum, no light curve, just a single epoch and several filters. We don't know what it was, but we just report it. It's the most viewed thing on TNS, so I guess that tells you just report things and you don't have to characterize them, it's fine. But this really started our whole goal of, hey, we should actually look more systematically for supernovae. We need programs to follow them up. We need resources that can only really be provided by James Webb. And so this started a cascade of many long and dire efforts that led us to sort of the first supernova survey that we did. And James Webb, not a very good survey telescope. I don't know if people have heard about this, but it's very expensive to do repeated observations with James Webb. The overheads are very high. If you just want to go and look at a supernova for maybe a half hour or something, it's going to cost you about 2 hours overall. And so that just adds up really quickly when you want to do an entire survey. These were at the time that we were doing this, kind of the large galaxy surveys. So this is just one visit, but over a large area of sky, large in the context of James Webb, which is at the high end here in terms of square degrees, this is about half a square degree. And then we go down from there, down to only 10 square arc minutes. So these are quite small in the context of things like ZTF and Rubin LSST and things like, and Euclid, all these large wide area surveys. But you should look at the depth side of this, which is going from 27th to 31st magnitude, kind of insane depths that are really only doable with James Webb. So we started here with the JADES surveys, which is one of these large galaxy surveys, large in terms of time, not very wide. It was such a large survey that they had to split it up over 2 years, the deep part of this. So they did half their exposure in 2022 and half in 2023. And that gave us the first opportunity to, in advance, know that, first of all, there was an opportunity to look for supernovae, and a wide, as in 25 square arc minutes, survey to look for supernovae. So this was what we did. Area of 25 square arc minutes, depth of 30th magnitude, and 9 filters ranging from 1 to 4 micron. So really a cool data set. And in only 25 square arc minutes, here's what we found. So this was the type of thing we were looking at. So we had 2022 and we had 2023. And there were two things we were looking for. There were things where the supernova was present in 2022 and absent in 2023. That accounted for, as you'd imagine, about half of the supernovae. And then there were things that were not there in 2022 and there in 2023, which of course is what we were interested in, because those were the live ones that we could actually follow. But note that even in this first set of things we were looking at, redshift 2.8, redshift 3.8, these immediately were the most distant supernovae that we'd ever seen, and due to both wavelength and sensitivity constraints, can only be followed by James Webb. So we had no other resources to throw at this. This was director's discretionary time proposals that we did repeatedly. And it gave us the opportunity to follow this field with additional visits to create light curves and get spectroscopy of a decent number of objects. So that's what I'll be starting with here. First of all, the 25 square arc minutes, this is the supernovae that Hubble would have seen had it been the one surveying this space. The size of the point is redshift, so bigger is closer, basically. So we would have found these nice 5 supernovae, and this is what we saw instead with James Webb. So you can see that this was a small improvement over what Hubble could see over this area. Looking at this in a more illustrative way is as a function of redshift. So this is brightness as a function of redshift for this same sample. The upper left is candles, the HST survey that was finding a lot of those high redshift type Ia supernovae in the past, with depths reaching about 27th magnitude. If you really push it with Hubble in a deep drilling field, you can reach down in this 28th, 29th magnitude, but over this large of an area, you wouldn't be able to do that normally. James Webb finding things down into the 31st magnitude regime and out to, as you can see, about redshift 5 in this 25 square arc minute area. So anything in this plot, by the way, with a horizontal error bar is a photometric redshift. Everything else has a spectroscopic redshift. So we've got about half and half because of the spectroscopic follow-up that we did in 2023, mainly. So this is the sample we got from JADES. So let me say something about this only works half the time, about the Type Ia supernova that we found in this field. So out of that sample, of course, we could only follow half of them, the ones that were in 2023. And because of the cost of observing things with James Webb, not in terms of the exposure time, but literally visiting there, we could only catch about 20 objects. So that's what we got out of this, was 15 to 20 objects. And of those, one of them was a Type Ia supernova. So 2023 ADSY is the official name of this one. So this guy was, you can see here, 2022 to 2023, you can immediately tell this one is quite red. And these are the difference images showing you there's clearly a transient here. The wavelengths of these goes basically getting to redder wavelengths this way and then this way. So the bluest is here at about 1 micron, and then this is the reddest at about 4 micron. So you can see immediately that this is quite a red object. This is the light curve that we got. It is a spectroscopic redshift of 2.9. So this is a nice redshift 3-ish supernova. And the reason that it was particularly interesting, for me at least, is it was the first one of these that was in that redshift greater than 2 high redshift possible Type Ia supernova regime when we followed it. So a couple things to note about the light curve. First of all, whatever you might be looking at this and thinking, it is the best observed high redshift supernova with James Webb. So it is expensive to do multiple visits. 4 visits is the most that we have yet done. So just keep that in mind. We do have 9 filters. I'm only showing 3 here, but there are 9 ranging from 0.9 micron to 4 micron. This is a Type Ia model fitting here, the blue here. And so you can see this is a nice fit. The really kind of crazy thing to keep in mind is look at the brightnesses. So this is 29th magnitude. And as I said, we 28, 29. And as I said, we did spectroscopy of this, and we got it on the last epoch. So it's right in this 28.5, 29th magnitude area. And this is the spectrum we got in the black. So it is on the noisy side, but 29th magnitude, not bad. The different colors here are a variety of different the supernova subtypes. So these are the best matches for each supernova subtype. So the top 3 are core collapse. So this is that type 2 hydrogen rich, and then type 1c, type 1b, these are the stripped envelope. And then two different type 1a types. So this is one that's calcium rich, and this one is just normal. So these are just kind of a variety of the best fit spectra. By eye, you might be convinced one way or the other. I can tell you statistically, the normal 1a is the best fit. But I would say it's not like 100% robust just from the spectra alone. If you put it next to these, I think you might feel a little bit better about it. I would say it's not any worse than something like than this. This is a reasonably convincing spectrum. But when we looked at this, we said probably a 1A, but could plausibly be 3 core collapse supernovae in a trench coat, masquerading as a 1A. And so we did go to some color magnitude diagrams, lots of things here. You don't need to worry about most of it other than to say, this is the 1A column and these are the core collapse columns. And basically just by glancing, you can see that the color evolution over time does not match well for at least one of the colors in each of the core collapse types, but matches quite nicely for a 1A. So between the color magnitude evolution as well as the spectrum, we kind of ruled out this 3 core collapse supernovae in a trench coat scenario. And this one does appear to be a type 1A at redshift 3. So that was our first one. The next one, 2023 AEAX, comes from the other end of the survey diagram, which is Cosmos Webb. It is shallower but wider, so it's half a square degree, but only about 28th magnitude only, but in the context of this, that is shallower. So this one, just visually, again, you can see is the exact opposite. It's very blue, it's brightest in these blue filters, and but we did the exact same thing. We looked for supernovae in this wide field. We found about 80 it wasn't actually 0.5 square degrees because it only overlapped with about 150 square arc minutes of previous imaging. So in a reasonably small area, we found 80 supernovae, and we again did a director's discretionary time proposal to follow up what we thought were the most interesting. This was one of them, a 1A candidate, and here's the spectrum we got. It's at redshift 2.2. And this one's a little bit better. I'm going to put this, oops, sorry, I put this on the side for comparison again. This is where we were at 1.6. And at 2.2, this was a pretty good match to a normal type 1A. So this one, a robust classification of type 1A at redshift 2.15. And in terms of the light curve, again, you won't be that impressed if you're kind of a ground-based survey person. But again, three light curve points, that's our game right now. So we have 6 filters in 3 light curve points, a couple filters with only 1 because it just depends on the program that was observing. But a couple of interesting things about these 2 type 1A supernovae, which are the first 2 spectroscopically classified 1As at above redshift 2. So the first thing that's interesting, which I kind of mentioned, is their color. So this is a distribution of normal ground-based, not ground-based, spectroscopically classified 1As that have been used for cosmology in the past. And the second one that I just showed, which I mentioned is blue, sits here. It's still within the distribution of normal cosmology useful 1As, but it is at the edge. And the other one that I mentioned was red, is over here. It's way off the edge of this, so it would be cut from ground-based samples, or not, I keep saying ground-based, but I mean cosmology samples in the past. But regardless, because these are the first 2 high redshift 1As that are in this regime that we're interested in, we said, all right, well, even though they would be cut from a low redshift sample, what happens if you just blindly standardize them with normal methods? So this is that same plot of our current sample, right, going out to redshift 1-ish, 1.5. And we can put them on this diagram, and this is where they land. So zoomed in up here are the edge of our photometric sample. This was the blue one that was found second, and the red one that was found first at redshift 2.9. So a couple of interesting things here. So let me pause on this for a second. First of all, the shaded region on this red line is the Hubble tension. So reminder of the Hubble tension, this is the 5 sigma or so discrepancy between measurements of the Hubble constant, so our current expansion rate, from Type Ia supernovae, which is in green, and CMB measurements using the standard cosmological model. So going back to this for a second, basically, you can see that these existing lower redshift supernovae, these are all biased a little bit low. That's because a high H0 is the bottom of this shaded region. And so the low H0 is the upper end. So basically, if you were thinking, oh, well, H0's definitely 73, then you might expect to be seeing all of these on the low end. Or if it's definitely 67, you might be seeing all these on the high end. The main point being, any shifts on this are not explainable by Hubble tension. So that's not the cause of these slight discrepancies. With only a few objects, of course, we need more, which is I will talk about at the end. You know, this is either low number statistics. It could be this guy's an absolute weirdo, which he does appear to be, but we will see. Or there is some little slope here going from biased low to biased high at high redshift. Cannot make any conclusions, but this is more data needed at the most extreme end. This could be the first indication of some sort of evolution, or on the more likely end, you know, this is just one statistical fluctuation. We will see these falling along this line in the future. I'll talk about that at the end, though. Here's my hard left turn to lens supernovae, so just take a breath and reset for a second. I will do a couple slides on the background of lens supernovae here to kind of refresh where we're at, because this is still supernovae, still James Webb, still high redshift, but a very different mentality and expectation here. So strongly lensed supernovae come about when you have some massive object, in this case a galaxy, but as you'll see soon, it very well can be a cluster of galaxies, between us and some source in the background. And when light from that source passes, it gets bent around this massive object, and that's the gravitational lensing effect. And in this case, from our perspective, we see 2 images of the same source in the background being split around this. When there are differences in those paths, whether it be geometric or differences in the gravitational potential, if the background source is variable, then you would see the arrival of that source at different times. And that difference in arrival time we call delta t, or the time delay. Which, if you can measure this, so the idea is you find something that's variable in the background of a gravitational lens, you measure it, you try and measure this time delay, and if you can, it's directly proportional to the Hubble constant. So this is another means of measuring the Hubble constant, and so another look at that Hubble tension, where these are the CMB and Type Ia measurements. The idea is, as far as I know, neither side is agreeing that the other side is correct. So we're going to keep measuring the Hubble constant with completely independent methods until we converge on one value or the other. So if we converge on Type Ia supernovae, then there's probably physics missing from the cosmological model. And if we converge on the CMB, then we probably are missing some significant systematics from Type Ia supernovae. The first measurement of the Hubble constant with a gravitational lens supernova is this one. So the supernova Restall, this was discovered in 2014. Not a Type Ia supernova, not that it has to be, but it was a core collapse supernova. And you can see that it's sort of on this low end, but with uncertainties that mean it is not really deciding anything between the two values. So the idea is, let's find more of these. So James Webb comes onto the scene and more or less immediately finds this. So this is a galaxy cluster, and this is 3 images of the same host galaxy here. So this is just one host galaxy, and it's at redshift 1.8. And these 3 little circles here, which you can kind of see from there, I hope, are a supernova going off in the galaxy at redshift 1.8. And we just happened to take an image when all 3 images were visible at the same time. And you can visually see the time delay happening here, because these 3 images of the galaxy, they look pretty much the same. So there's relatively the same magnification, but yet this image much brighter than this image, and this one's sort of in the middle. showing you that one of these images is close to peak brightness, whereas the others are further from peak brightness because of this relative time delay, meaning this one arrived first, then this one, then this one. So another director's discretionary time program, you can see the theme of many proposals over the last couple of years to follow this object, and here's what we saw. So here's our three images, A, B, and C, and then here's our corresponding light curve. So again, three light curve points, but because the different images are at different phases of the supernova evolution, we could put them on a single light curve. And so this is the central image, which is why it's brightest. It's closest to peak. So basically, if you could play a movie, you would see first the red images appear and then fade, then the green appear and then fade, and then the blue appear and then fade. And the snapshot that we got is when the red already faded, green was in the middle, and blue is near peak. That's the snapshot we got. And we could put them on a single light curve like this, and that gives us our time delay measurement, as I'll show in a second. We also did one visit of spectroscopy. So we got one, on the first visit that we followed up with, we did a spectrum of each of the images, which basically in a single visit gives you the spectral evolution of the supernova. One visit, three spectra, three different timestamps. So this one is right near peak. You can see here's the silicon that we look for. This is again a Type Ia supernova at redshift 1.8. So we get basically near peak. This one is around 20 rest frame days after peak, and then this one's around 50 rest frame days after peak, which basically looks like noise, but it's not quite. So in terms of single snapshot spectral evolution, that's really cool. It also enabled a spectroscopic time delay measurement, basically by figuring out what phase the supernova is at by its spectral evolution between these two phases. This enabled the first Type Ia supernova Hubble constant measurement. Uncertainties are relatively large, that's this one, but that's mostly because we do not have a template. We have no images of this supernova when it has faded, which means the photometry is really difficult. The host is very bright. And so we have a new program to come back in the spring, subtract off the host, redo this measurement, and these error bars should shrink nearly in half. But you can see it comes in on the high end, uncertainties again, too large to really fully distinguish between these. So the next really cool thing that we found with James Webb, this is a Hubble image. It's about to get way cooler with James Webb. This is a Hubble image of another cluster. It was discovered in 2016 with another triply imaged supernova here. We called it supernova Requiem. And the central image you can see again is bright and blue, whereas these are both red and faint. So it's a similar scenario where the central image is close to peak brightness, and these two are further. And this cluster was reobserved by James Webb in 2023, unrelated to the supernova. And lo and behold, the same galaxy had another supernova in it. So you can't actually see it from this scale, but in the paper, if you want to look this up, we zoom in on these, and but these circles are circling three images of another supernova. Same host galaxy, these are both at redshift 2, and they are both Type Ia supernovae. So the chances of this were very small, but we happened to catch, this is the first instance of one galaxy hosting two multiply imaged supernovae. It's the highest redshift sibling pair of Type Ias at redshift 2. We have spectra showing that this, similar to what I was saying before, is relatively normal for supernovae compared to low redshift, at redshift 2, still pretty normal. And then the final really cool thing about this system is that supernova Requiem, discovered in 2016, is going to reappear here in image D in 2026. So we're actually very close to reobserving this system in the next couple of years. And we know when and where a Type Ia supernova is going to explode. I challenge anyone else to do the same. And then Encore will then follow it up several years later. So obviously a very cool system. We are currently measuring the Hubble constant with supernova Encore. We do everything blinded, can't show any results. But within the next few months, probably. The uncertainties, it's a similar scenario to supernova Hope. we need a template to do better photometry, better time delay measurements. So the uncertainties will be about the same. But we hope to, we put in a proposal, of course, to do a template image of that. So it should improve things. And then when supernova requiem reappears in this image here, we can do a joint Hubble constant measurement. So this has a 10-year time delay, so it should be a very high precision Hubble constant measurement, and the first where we could do 2 Hubble constant measurements in the same host cluster. So this one is a very cool system. Okay, so where's our next efforts going? So this NIRCam surveys slide, there's a new one starting in May. It's called Nexus. And the reason we're excited about Nexus is you can see it's not as wide as Cosmos, it's not as deep as Primer, but the reason we're excited about it is because it's the first time domain survey. So it is 3 years of repeated observations every 2 months. We also put in another proposal to increase that cadence to every month. So we'll see if that works. But what they're going to do is every 2 months they observe the same patch of sky, and then they also get about 1,000 spectra using multi-object spectroscopy of all the sources that are interesting in that patch of sky every 2 months. So we will get time series spectroscopy of a variety of transient objects, as well as light curves that have more than 3 points in them, because we're actually observing this repeatedly for 3 years. It's also our first opportunity to look for the really high redshift long variability objects where you need to visit the same region of sky for several years to see things changing. So we're really hopeful that this will be our first big chance to kind of build a sample of all these different high redshift objects with James Webb. It's starting in May, like I said, so we're really right around the corner. And push to really high redshift, things that you need to be following over the course of like years, not months. And then this is a program that I'm running over the next 2 years, basically to do this. We have 10 target opportunity triggers over the next 2 years to fill out this high redshift area of this diagram. So we will hopefully go from 2 to 12 in the next 2 years, and basically get our first real statistical answer to what exactly is happening at high redshift to Type Ia supernovae. And we hope to basically use that Nexus program as a detection program and then follow it up with this one, getting extra spectroscopy, extra imaging. So we're planning on kind of playing those off of each other. In coming years now, we have the Roman Space Telescope. So this is launching in 2026, and it is an infrared space telescope that will have a time domain survey whose main goal is to do Type Ia supernova cosmology. And you can see that in this redshift 1.52 plus, it's really filling in the Hubble diagram. So doing a combination of really precise constraints on dark energy and to some extent answering this question of Type Ia evolution, as well as a wide variety of non-1A transient science will be, this is what I'm mostly excited for in the next few years. One interesting thing to note is that similar to Hubble, while it will be able to observe things out to redshift 3 and beyond, spectroscopy of these objects is still going to be limited to James Webb at the moment. There is a spectroscopy with Roman, but it's not going to be able to do anything in this high redshift regime, which means we're going to have to continue putting in James Webb proposals. And as we saw in this year, this is showing all Hubble proposals of all time. Time left until deadline, this is just for our internal fun, but basically you want to see how high we ended up. And then first cycle, second cycle, third cycle, fourth cycle, I don't know. We're getting way up there. So we're worried about resources, of course, but we will continue to try and get the resources that we need from James Webb to build our high redshift spectroscopic sample. On the lensing side, Roman plus Rubin and the LSST will combine for quite an interesting sample, with Roman providing mostly higher redshift gravitational lens supernovae and Rubin at the lower end. Roman, the exciting thing about this is because it's got the time domain survey, it will simultaneously give you very nice light curves for all of the gravitational lens supernovae that we observe, as well as the resolution needed to resolve multiple images, even in compact systems. So again, very excited about Roman for lens supernovae. So that's the summary, which is that we're basically finding the first high Z supernova with James Webb, and the next year or two, this should really ramp up to statistical samples, but we're getting our first peak. We have observed many core collapse supernovae. This is not exactly what I do, but you can ask me about it, and I have some slides that I can pull up as well. There have been two cluster lensed gravitational lens supernovae that happen to both be Type Ias that were detected by James Webb. Both are providing measurements of the Hubble constant, which will increase our sample of Hubble constant strong lens supernovae from 1 to 3. And we also have a program to expand that sample from 3 to 6. We have programs between Nexus and my follow-up program to build this Type Ia sample over the next couple of years with more spectroscopy, more light curve points, more filters. So we should go from 2 to maybe 15 or 20 in the next year or two. So that will be very exciting. And we have a very good future with Roman in particular for both high redshift supernova discovery, strong lens supernovae, everything in the kind of rare high redshift time domain world. Yep, that's it. Thank you.
Yeah, this seems like a really good subject, and 30 years ago.
Okay. We do. Yeah. Okay, yeah. So on the core collapse side, most of what we see is core collapse. As I said, we have 80, 100 supernovae, and we only have 2 1As. So where are all the other ones? So I could show you some slides, but so the interesting stuff that we've found mainly is so the first cool thing that we found was this redshift 2.8 1C broadline. And it was in the first set of spectra that we got of any supernovae at high redshift, which was a little weird by itself that this was one of the first things that we saw. In terms of its other properties, it has very high ejective velocities, it has low metallicity and in the host, and is making the people that in our group that are interested in this type of thing wonder about relative rates of things like 1C broadlines at high redshift if it's one of the first things that we saw. You might think about bias, these things are bright, but we were like 4 magnitudes, limiting magnitudes below these types of things that we were looking at. Let me go over here. We have this. This one. Kind of ignore the various epochs, but the main thing is this is a redshift 3.6 type 2, and the detection epoch here you can see is extremely blue, coming in this 2,000 to 3,000 angstrom range. And if you do a combination of temperature measurements, which says this thing is very young, and spectroscopy, which says this thing is very young, we found like a redshift 3.5 type 2 supernova that's within a few days of explosion in the rest frame. So that was a very cool one. We have a couple of nebular phase spectra of redshift. This one is at redshift 1.5. Yes. That is, sort of, we have a few of these that we haven't really dug into, but we have a series of like redshift 1.5 to 3 nebular phase spectra that we're still kind of figuring out. And then we also have this redshift 2 type 2 that was tricked us. We thought it was a 1A in a redshift 2 quiescent galaxy that we thought was going to be 1A based on both host properties and the early light curve, which turned out to be this pretty nicely observed type 2. So, and then we have a bunch of very high signal to noise, redshift 1 to 2 type 2 spectra that I didn't show, but we have them. and a series of redshift, basically like 3.5 to 4.5 light curves of type 2s. So that's kind of the high level sample that we have so far. We're doing rates analysis with these. We're doing IMF constraints and kind of metallicity, massive star, high redshift constraint, or like, relationships as well. That's like the big picture of where we're at with those. Back to here. Yeah, yeah, right. Yeah, so I mentioned at the beginning, the progenitor system question is like, for 1As, I said they're in a binary system, but we don't know whether they are single degenerate, meaning the companion is not another white dwarf, or double degenerate, they're both white dwarfs. And then also the delay time is, the other question of how long it takes from formation to explosion, basically. Yeah, so we're, again, too soon to say exactly, but we are, for things like Nexus, where we have an actual survey over a real amount of time, we're going to be sensitive to high enough redshifts where if we don't find any redshift, say 6 or something 1As in that time, then we can start to rule out, prompt 1As and various progenitor channels at that point. With such a small sample in such a small area, we're still in the regime where you can still say, oh well, they're just rarer. In this sample of jades, we were sensitive to redshift, whatever number you want, at 31st magnitude. But I mean, didn't see anything, but it's only 25 square arc minutes, so that all that tells you is every supernova isn't in that progenitor channel. But yeah, it's still a little early to say. But Nexus is going to be good for this. Yeah, it is just chance, actually. You might think that it wouldn't be chance if we were doing some sort of survey and we were, only the peak brightness is above our detection threshold or something like that. Then yeah, that would be, we're only seeing them at peak brightness because that's what we need in order to detect them. But in this case, these are pure chance. The two surveys, or this supernova hope, they had nothing to do with time domain, nothing to do with supernovae. They were just trying to do cluster observations for galaxy science. So they just got scheduled whenever Space Telescope could schedule it, and it just happened that they were both right next to brightness. So yep, pure chance, and also pure chance that we're even seeing multiple images at the same time, right? Like if we had observed this one, maybe a month later, we probably just wouldn't have detected this, since it was close to the end of its evolution, as you can see here. And if we'd observed it a month earlier, we would have seen, this one at peak brightness instead. So pure chance, but we've been pretty lucky. Time dilation helps you a lot. At redshift 2-ish, right? A normal type 1A supernova is lasting for a couple months. So it becomes 6 months at redshift 2, and that's very helpful. But the relative time delays here for these ones are on the order of 1 to 4 months. And so, if you detect this one at peak brightness, this one is already several months down the road. And so, yeah, if we'd been a couple months later, we would have just missed one of them. So it's been very lucky, and we were able to do a lot with these couple of systems. Yeah, not really. So the issue with this is because the resources for follow-up are so limited, we basically are heavily biased, not towards brightness as you might be from the ground in terms of spectroscopic follow-up, but just we follow the most clustered set of supernovae. So we want to get as many things as possible. It's a new type of bias. And so we're basically saying, okay, we found 80 supernovae. If we point here, we can observe 4 interesting things that we think are interesting and 10 things that we don't really care about, but we'll get spectra for. If we point over here, we can only get 1. So we're going to point over here. And that's what we've done so far. And so it just so happens that the clusters we've pointed at, we have prioritized getting at least one 1A candidate, which has worked twice. But we would need more things to more resources. And that's what Nexus is going to do. So Nexus is over this whole area that it's observing. The whole area is being observed with both imaging and spectroscopy, with multi-object spectroscopy. So anything that you're getting a light curve of, you can in principle get a spectrum of. And so in that case, we get a real survey volume and a real set of rates, which is really, it's one of the focuses of the program. And so at that point, we should be able to answer questions about high redshift rates much better, as well as progenitor channels. So this is what we're kind of waiting for. It starts in May, as I said. Yeah, so at these redshifts, greater than 2 or whatever, we're probably not going to add meaningfully to the changing dark energy discussion. That's really going to be Roman and Rubin, where the main focus is redshifts less than 1.5. But the evolution side is really what we're focusing on with James Webb. And the answer is basically how much evolution do you want to rule out? So to get down to about, say 10%, which is like the intrinsic variability of 1As already, that's the level you need, is about 20. So it's reasonably high leverage at that point. You don't need 100 or 1,000. You need like 20 to get to that 10%-ish level. If you want to do a 1% constraint, that's going to take a while. Yeah.